The iPhone Air's battery is not just thinner, it's geometrically revolutionary in a way that traditional manufacturing cannot compete with. Metal can cells let you fill any 2D space, meaning Apple can now extract 20-30% more capacity from the same physical device. This single innovation just created a technological moat so wide that Samsung and Xiaomi are now facing a production nightmare they didn't anticipate. But the real shock? This architectural change opens a pathway to silicon anode batteries that store 50% more energy than graphite, and nobody in the industry is ready for the supply chain chaos that comes with scaling that. When Apple announced the iPhone Air in September 2025, the design team revealed something that seemed almost mundane, a new battery architecture. Journalists obsessed over the 5.6mm thickness. Tech reviewers measured charging speed. But the material engineers, the ones who actually understand battery physics, immediately understood what had just occurred. For decades, smartphone batteries have used pouch cells. Picture a flexible plastic envelope filled with electrodes, separators, and liquid electrolyte. The design is cheap to manufacture and reasonably safe, but it has a fatal weakness: swelling. Every lithium-ion battery swells during charging. That expansion is baked into the chemistry. In a flexible pouch, you need buffer space. The corners of L-shaped batteries, which have been standard in iPhones for years, become pressure points where internal stresses accumulate. You need padding. You lose capacity. Apple switched to metal can cells. Imagine a rigid aluminum can surrounding the entire battery stack. This single architectural change does something profound. It distributes expansion stress evenly across the rigid structure instead of concentrating it at corners. Gene Berdichevsky, the co-founder of Sila, which supplies silicon anode materials to major battery manufacturers, told TechCrunch that this is pretty revolutionary. His exact words: "You can now build batteries in any two-dimensional shape you want. Those are very finicky with pouches, and this basically makes it bulletproof." Well, what does that mean in dollars and engineering terms? Apple's battery partners, primarily ATL, Sunwoda, and Desay, can now fit 20-30% more energy into the same physical footprint without increasing weight or thickness. The iPhone Air battery is notably smaller than previous models' batteries, yet the device maintains competitive battery life. That efficiency gain doesn't come from magic. It comes from a mechanical architecture that companies like Samsung and Xiaomi are not equipped to manufacture at scale. This is where the supply chain disruption begins. The shift from pouch to metal can cells requires precision stamping, laser welding, and tolerances tighter than what pouch cell manufacturers have ever needed. We're talking about equipment investments in the hundreds of millions of dollars per facility. ATL, Apple's primary battery supplier, has the expertise and capital to make this transition, but smaller competitors do not. Here's the real-world impact. As of January 2025, KTL and BYD collectively control 55% of global EV battery installations, with KTL alone at 38.1%. These companies have invested heavily in LFP, lithium iron phosphate batteries, which are cheaper and safer but lower in energy density. They are not positioned to mass manufacture metal can cells at the scale needed for flagship phones. That means Apple's innovation creates a widening gap where high-end consumer electronics require metal can architecture. But the companies dominating cell production are chasing volume in LFP and semi-solid state batteries. The competitive imbalance is stark. Apple can work with ATL. Samsung and LG Energy Solution have their own manufacturing, but they're behind on metal can scaling. Xiaomi, OnePlus, and dozens of mid-tier phone manufacturers have no metal can capacity whatsoever. They face a choice: wait 2 to 3 years for secondary suppliers to build capacity, or accept lower energy density and slower innovation. That lag matters. Because metal can architecture is more than just a design upgrade, it's a Trojan horse for the next generation of battery chemistry. Silicon anodes, the infrastructure race. Here's what industry insiders understand, but most analysts miss. Metal can cells are purpose-built to accommodate silicon anode materials. Pure silicon anodes can store 50% more lithium than traditional graphite anodes. But silicon has a problem. It expands dramatically during charging cycles. That expansion has historically destroyed battery performance within 500, 800 charge cycles. With a rigid metal can constraining the expansion uniformly, silicon swelling becomes manageable. Companies like Sila, Group 14 Technologies, and Enovix have already demonstrated that silicon-carbon composite anodes can achieve 1,000-plus stable cycles. But they've only done this at small scales, wearables, prototype devices, limited production runs. The manufacturing capacity for silicon-carbon anodes globally stands at roughly 150,000 metric tons annually as of 2023. Industry analysts project that figure will need to reach 300,000 metric tons by 2030 to meet smartphone and EV demand. That's a 100% expansion in capacity in just 5 years. Group 14 is building a 4,000 ton per year facility in Washington state. Sila is scaling production in Moses Lake. But the vast majority of capacity expansion will happen in Asia, particularly China. This is where geopolitics collides with chemistry. China already controls 80% of global battery-grade lithium hydroxide processing. They dominate refining for cobalt and nickel. And now, as silicon-carbon composite anode materials scale, Chinese suppliers are racing to establish processing monopolies. The supply chain for the next generation battery isn't being built in Silicon Valley. It's being built in Shenzhen, Chongqing, and Sichuan. What Apple has engineered, quite cleverly, is a forcing function. By deploying metal can cells in mass production, the iPhone Air was manufactured in the millions in Q3 and Q4 2025. They've created immediate demand for the manufacturing infrastructure that supports silicon anodes. Competitors who don't adapt quickly face a compounding disadvantage. Each quarter, Apple sells more metal can devices. The supply chain becomes more entrenched. Prices come down for Apple's partners, and the cost disadvantage for laggards grows. Global mining, the cobalt and graphite crisis. Now here's where this gets economically dangerous at a global scale. The shift from pouch to metal can cells doesn't change lithium demand dramatically. Both architectures use lithium at similar rates. But the supply chain of cobalt, nickel, and especially graphite faces severe dislocation. Cobalt is the most precarious link. Roughly 70% of global cobalt production comes from the Democratic Republic of Congo, where labor practices are questionable, environmental controls are weak, and geopolitical risk is high. Cobalt prices spiked to $19, 136 per metric ton in January 2025, a function of both EV demand and supply nervousness. The supply chain is so concentrated that any significant disruption, a mining accident, an export restriction, a labor strike, propagates globally within weeks. Apple has committed to using 100% recycled cobalt in batteries by 2025. This commitment is partly environmental posturing, but it's also pragmatic supply chain hedging. By building battery recycling infrastructure through its Daisy robot program, Apple reduces dependence on mined cobalt. But this creates a secondary market that other manufacturers can't easily access. Apple's recycling priority means less recycled cobalt available for competitors. Graphite is the underappreciated crisis. The U.S. currently has zero domestic graphite production, despite graphite being one of the largest inputs in lithium-ion batteries. A 50 kilowatt-hour EV battery requires 100 kilos of graphite, more than the combined weight of lithium, manganese, cobalt, and nickel needed for that same battery. This is not a minor material, it's foundational. Global graphite supply comes primarily from China, 65%, Brazil, 12%, Canada, 8%, and Australia, 5%. China also controls much of the processing. The Inflation Reduction Act and Biden administration have prioritized graphite as a critical mineral, and in October 2025, the federal permitting process granted a 13.5-month timeline for the Graphite Creek deposit in Alaska, which represents North America's largest natural graphite resource. But 13.5 months to permitting is not the same as 13.5 months to production. The actual mine could take 3.4 years to come online. What does this mean? For the next 2-3 years, graphite supply is inelastic. Demand from EVs is accelerating. Demand from smartphone batteries will increase as silicon anode adoption spreads. And supply from traditional sources is geographically concentrated and politically risky. Graphite prices, which fell during the 2023 battery overcapacity crisis, are set to spike as AI-driven computing, EV scaling, and silicon anode adoption converge. Apple's metal can architecture doesn't directly increase graphite demand. Both pouch and metal can use graphite at similar rates, but the enabling of silicon anodes does. As silicon content in anodes increases from current levels of 5 to 10% toward 30 to 50%, graphite still remains a critical component of silicon carbon composites. The supply pinch becomes severe. Manufacturing reshoring, the geopolitical reversal. Here's something most people have missed. Apple's metal can battery strategy is intimately connected to the Biden administration's reshoring agenda. In late 2025, Apple announced a $600 billion commitment to expanding U.S. semiconductor and component manufacturing. This isn't charity, it's supply chain de-risking. The company is investing in rare earth recycling facilities in Mountain Pass, California, semiconductor manufacturing in Texas, Utah, and Arizona, and battery component manufacturing in multiple states. In 2025 alone, Apple's U.S. supply chain was on track to produce more than 19 billion semiconductor chips domestically. The Inflation Reduction Act has made it fiscally attractive for Apple to develop North American battery manufacturing capacity. But here's the catch. Building a metal can cell factory is exponentially more complex than building a pouch cell factory. You need precision stamping equipment, laser welding systems, and quality control infrastructure that doesn't yet exist at scale outside Asia. This creates a window of opportunity for a few years. The companies that can move fastest to establish metal can capacity in the US or Mexico gain competitive advantage in IRA tax credits. The companies that wait risk being locked out of North American battery supply for years. ATL, Apple's primary supplier, is a Chinese company. The geopolitical implication is stark. Apple depends on Chinese manufacturing for its most advanced battery technology. But at the same time, Apple is funding the development of competing North American capacity. This is not a contradiction. This is calculated portfolio hedging. If USI-China relations deteriorate further, which the October 2025 rare earth export restrictions suggest they will, Apple ensures it has alternatives. And in the process, Apple is forcing other manufacturers to make similar bets, which accelerates the entire shift. The Department of Defense has explicitly identified battery materials and manufacturing as critical national security issues. The US government has begun directly investing in graphite, lithium, cobalt, and nickel supply chains. These investments, combined with Apple's reshoring push, are creating a bifurcated global supply chain where Western manufacturers are slowly decoupling from Chinese processing, but at significantly higher costs and lower efficiency. This decoupling has enormous implications for battery prices. Chinese cell manufacturers compete ferociously on cost. Western manufacturers, operating at higher labor costs and newer equipment, cannot match that cost structure. As battery supply splits between Western-controlled capacity and Chinese-controlled capacity, prices will diverge. High-performance metal can cells manufactured in North America or Europe will cost 15-20% more than equivalent cells manufactured in China. This price premium will flow to premium devices, Apple products, high-end Samsung phones, select gaming devices. Mass-market phones will continue to rely on cheaper, lower-density Chinese cells. That segmentation restructures the entire smartphone market. Silicon battery market, the next trillion-dollar bet. The silicon anode battery market was valued at roughly $122 million in 2025. Industry projections forecast it reaching $834 million by 2030. That's a 47.5% compound annual growth rate. But those numbers obscure something crucial. The market isn't growing gradually. It's shifting discontinuously. When metal can cells reach 30-40% market penetration, which could happen by 2027, 2028, the viability of silicon anodes improves dramatically. Fewer companies will want to invest in traditional pouch cell infrastructure if they know metal can is becoming dominant. That creates a cliff-like transition where capacity investment suddenly accelerates. Mercedes-Benz, Panasonic, and Sila recently signed multi-year offtake agreements covering 1 million cars annually starting in 2026. These agreements are essentially bets on silicon anode scalability. They commit to purchasing volumes at prices that force suppliers to build capacity ahead of demand. If those agreements are fulfilled, silicon anode production will jump from token volumes to commercially significant quantities in 18 months. Here's where Apple's influence becomes subtle but powerful. Apple's metal can adoption signals to the battery industry that silicon anodes are not speculative, they're inevitable. This shifts supplier behavior. Smaller players accelerate R&D investments. Larger players begin building capacity in anticipation of Apple's next generation of devices. The entire industry coordinates around a technology transition without any explicit coordination. This is supply chain herding. Apple sets the direction. Everyone else follows because the cost of not following is competitive obsolescence. Environmental paradox, sustainability and complexity. Here's the uncomfortable truth that nobody wants to say out loud. Apple's push toward higher energy density batteries and advanced manufacturing does reduce per-device environmental impact. But it dramatically increases supply chain complexity and geopolitical risk. Metal can cell manufacturing requires more precision and more energy than pouch cell manufacturing. The equipment is more capital intensive. The quality control requirements are more stringent. Early environmental analyses suggest metal can cells require 8 to 12% more energy to manufacture than pouch cells, though this is offset by superior thermal characteristics and longer lifespan. But here's the second-order effect. As battery energy density improves through silicon anodes and advanced architectures, devices can become thinner and lighter. Thinner devices require more sophisticated materials and manufacturing processes, which typically have higher environmental costs initially. Apple's 3D printed titanium components on the iPhone Air, for example, use 33% less raw material than traditionally machined parts, but require more specialized energy and equipment. On recycling, Apple's commitment to 100% recycled cobalt by 2025 is genuine and consequential. The company has built massive recycling infrastructure through its Daisy robot program, which disassembles old devices and recovers valuable materials. Recycling cobalt reduces emissions by 80-90% compared to mining new cobalt. But The implication is that Apple is building a closed-loop system where they control material flows, and that creates competitive advantages for them relative to manufacturers without similar recycling infrastructure. This is where environmental sustainability and competitive advantage converge. Apple's recycling infrastructure becomes a moat. Competitors cannot easily replicate it. Over time, Apple devices will use progressively less newly mined material, lowering their supply chain risk and environmental impact. Other manufacturers will remain dependent on primary mining, facing both higher costs and higher geopolitical exposure. Market disruption. Who wins and who loses? Let me be specific about the winners and losers. CATL and BYD, the two dominant Chinese battery manufacturers, are facing an awkward strategic position. They have massive installed capacity for LFP cells, which dominate the EV market. LFP is superior for cars. It's cheaper, safer, and has longer cycle life, but LFP's energy density is lower than lithium-ion with nickel cobalt. For smartphones, where weight and thickness matter, LFP doesn't work well. Apple's shift to metal can cells essentially concedes the premium smartphone battery market to manufacturers with advanced lithium-ion capabilities. ATL, Sunwoda, Desay, and perhaps LG Energy Solution, and Samsung SDI. It means CATL and BYD, despite their dominant EV position, have limited leverage in high-end consumer electronics. LG Energy Solution and Samsung SDI, by contrast, are breathing easier in the short term. Both have advanced lithium-ion capabilities and relationships with premium phone manufacturers, but neither has the scale that ATL has, and both face margin compression as battery prices continue declining. LG Energy Solutions' market share fell from 11.1% in 2024 to 9.3% in January-October 2025, primarily because Tesla shifted toward LFP batteries and other suppliers. Samsung SDI is experiencing similar pressure. Smaller players, the second-tier battery manufacturers that supply regional phone makers, are effectively locked out. They cannot afford the capital investment required for metal can cell manufacturing. They cannot compete on price with established players. Their viable market becomes increasingly constrained to budget phones using older pouch cell technology. This consolidation in the battery industry is profound. Where the market was fragmented across dozens of suppliers, it's consolidating around 4 or 5 global leaders. This consolidation increases pricing power for those leaders in the short term. They can extract more margin as they move up the value chain toward premium products. But in the long term, this consolidation creates fragility. If a single supplier, say ATL, faces disruption through geopolitical tensions, natural disaster, or operational failure, the entire supply chain for premium devices becomes vulnerable. Rare earths. The geopolitical chess match. China's October 2025 rare earth export restrictions deserve more attention than they've received. Rare earths are used in motors, magnets, and various electronic components throughout smartphones and consumer electronics. China controls roughly 70% of global rare earth mining and over 85% of processing. When China announced restrictions on 12 of 17 rare earth elements, it was a direct message. Technology supply chains that rely on Chinese processing are subject to Chinese geopolitical leverage. Apple specifically announced targets for 100% recycled rare earth elements in device magnets by 2025. This is partly hedging against exactly this kind of supply restriction. By recycling rare earths from old devices, Apple reduces direct dependence on primary mining and processing. But this recycling doesn't happen at scale for other manufacturers. Xiaomi, Oppo, Vivo, all major Chinese phone makers, ironically, remain heavily dependent on primary rare earth supplies. Here's the asymmetry. Apple's higher margins allow it to invest in recycling infrastructure and supply chain resilience. Smaller competitors cannot afford these investments. So as China tightens control over rare earth supplies, Apple's competitive position strengthens through vertical integration and infrastructure investment. The US government recognizes this. The Rare Earths Exchanges Initiative, announced in late 2025, explicitly aims to break Chinese dominance in rare earth processing. Companies like USA Rare Earth and others are receiving government support to build processing capacity outside China. But again, this is a 3 or 5 year project. In the interim, supply chain fragility increases. Supply chain implications. Cascading failures. Let me walk you through how a realistic supply chain crisis would unfold. Scenario. In Q1 2026, geopolitical tensions between the US and China escalate. China restricts exports of graphite and rare earths. It's not an outright ban. That would be too economically damaging to China itself. It's a licensing regime where exports require explicit approval, which will slow approvals by 3 to 6 months. Immediate effects. Smartphone and EV manufacturers face a 3 to 6 month delay in sourcing graphite and rare earths. Prices spike 30-50% because buyers panic and try to secure months of supply ahead of time. Smaller manufacturers with no strategic stockpiles are forced to halt production or accept shortages. Secondary effects. Apple, which has invested in North American graphite production, Graphite Creek, and rare earth recycling, experiences minimal disruption. In fact, Apple's supply position improves relatively as competitors struggle. Phone manufacturers more dependent on Chinese supplies, Xiaomi, Oppo, Vivo, face production constraints. Samsung and LG, which have supply diversification, muddle through with margin compression. Tertiary effects. EV manufacturers face severe constraints because they use 100x more graphite than phone manufacturers per unit. Tesla, which has some supply diversification, decelerates production slightly. Chinese EV makers using CATL batteries face more severe constraints because they have less supply diversification. The global EV market experiences a 3 to 6 month slowdown. That slowdown propagates through the entire automotive supply chain, semiconductors, motors, interiors, and creates knock-on disruptions for months afterward. This scenario isn't speculative. It's based on actual geopolitical tensions, actual supply concentrations, and actual supply chain fragility that's documented by government agencies, including the US Department of Energy and the European Commission. The investment thesis? Who should care? If you're an investor in battery makers, this is the macro context. CATL and BYD control EV supply, but ATL, Sunwoda, and DESE control premium smartphone and high-end consumer electronics supply. That's a smaller market, but it's higher margin and more strategically important. Apple's metal can adoption validates that silicon anode technology is commercially viable, which accelerates investment in companies supplying silicon anode materials. Group 14 technologies, Sila, Enovix. Within 18 months, we'll know which of these companies can scale to profitable volumes. The ones that can will be worth billions. The ones that can't will consolidate or disappear. If you're a smartphone maker, you're facing a strategic fork. Either invest heavily in advanced battery manufacturing capabilities, or accept that your flagship products will be technologically inferior to Apple's and increasingly unable to compete on key metrics. That's a painful choice, which is why Samsung is making noise about scaling silicon anode capacity, and why Xiaomi is aggressively pursuing relationships with ATL. If you're a mining company or a critical minerals processor, this is a demand growth narrative. Lithium, cobalt, and nickel demand are growing faster than supply can expand. Graphite supply is particularly tight. But this growth is also increasingly subject to geopolitical disruption. Companies with diversified supply chains and processing in multiple countries will outperform companies with concentrated operations. If you're a government policymaker, this is a national security issue disguised as a commercial technology transition. Control over advanced battery manufacturing and critical minerals processing is strategic power. Countries that move quickly to develop domestic capacity will gain leverage over countries that remain import dependent. The Inflation Reduction Act is explicitly designed to solve this problem. Success will reshape global supply chains over the next decade. Scenario analysis. 3 possible futures. Scenario 1, the decoupling path. Over the next 3 to 5 years, Western governments successfully build out domestic critical minerals capacity and battery manufacturing. North American graphite, lithium, cobalt, and nickel production increases significantly. Metal can cell manufacturing capacity is established in the US, Canada, and Mexico. Apple and other Western tech companies reduce their supply chain exposure to China from current levels, 90% plus for assembly and key components, to something like 40-odd to 60%. Outcome, higher costs for consumers. Battery prices and device prices increase 8 to 15% because Western manufacturing is more expensive than Chinese manufacturing. But supply chain resilience improves. Geopolitical risk declines. The tech industry becomes less dependent on a country that is simultaneously a strategic competitor. This path is economically expensive but geopolitically safer. Scenario 2, the hybrid path. Western governments build some domestic capacity, but not enough to fully decouple from China. Critical minerals processing remains partially dependent on Chinese capacity. Battery manufacturing splits between Western capacity, high-end metal can, and Chinese capacity. Volume, LFP. Supply chains stabilize at a new equilibrium, where China retains 50 to 60% of global battery manufacturing, but higher margin advanced manufacturing moves west. Outcome, moderate cost increases. Supply chain fragility remains, but at a lower level. Geopolitical tensions continue to spike periodically as China uses supply restrictions as leverage, but these restrictions don't become existential threats. This is the most likely scenario given current policy trajectories and economics. Scenario 3, the China dominance path. Geopolitical decoupling fails. Western governments don't move fast enough to build meaningful domestic capacity. Chinese battery manufacturers, CATL, BYD, continue to dominate globally, including in premium segments. They rapidly adopt metal can technology and silicon anodes. Apple and other Western manufacturers remain dependent on Chinese supply. Outcome? Lower costs in the short term, more innovation competition in battery chemistry, but severe geopolitical risk for Western tech companies. If US-China tensions escalate to sanctions or export restrictions, Western tech companies face supply shocks that could halt production for months. This risk discount would likely reduce valuations for Western tech companies. My assessment: Scenario 2 is most likely. We're already seeing it unfold. Western governments are moving to build capacity, but not fast enough to achieve full decoupling. China will retain dominant positions in processing and volume manufacturing, but premium advanced manufacturing will gradually shift west. This transition creates a 3 or 5 year period of elevated supply chain risk before equilibrium is reestablished. The conclusion? What this means for you. Here's the meta pattern I want you to see. Technological innovation at scale always triggers supply chain disruption. Apple's move to metal can cells is a seemingly small architectural change, with outsized supply chain implications. What makes Apple dangerous, and I mean dangerous in a competitive sense, is that they can absorb the disruption. They have capital, vertical integration, supply chain resilience, and relationships with Tier 1 suppliers. The disruption that paralyzes a mid-tier competitor barely slows Apple down, and in the process, Apple's competitive advantage widens. This is the pattern that has made Apple one of the world's most valuable companies. They don't just make products. They restructure supply chains in ways that benefit them and harm competitors. The metal can battery revolution is just beginning. As metal can cells scale from 5 to 10% market penetration today to 40, 50% in 2028, 2029, the suppliers who can manufacture at scale win. The suppliers who can't, don't. This consolidation will reshape the entire battery industry. And here's the final implication. The next generation of devices, not just phones, but watches, tablets, AR glasses, robotics, will increasingly be constrained by energy density. That means silicon anode adoption is inevitable. And silicon anode adoption is enabled by metal can architecture, which means the architectural shift Apple just made isn't a temporary competitive advantage. It's a forcing function that reorganizes the entire industry. This is supply chain economics at scale, and nobody outside of industry insiders is paying attention.